Well, why do we have an antenna? Inside an AP or some radio device, we have the radio amplifier, the one that's creating the RF energy, okay? The amplifier inside. Now we have to get that out to wherever we want it to go, okay? So we have these things called antennas. That's what they're for. Now, antennas and antenna gain are often misunderstood, and this is a big problem. A simple antenna, in fact better than that, an energy source we can think of as the sun. I'll draw that in red, because I've got red. Right? That is the sun. Just imagine, I don't know. Right. That's the sun. The sun is a unique transmitter. Now, lots of things come from the sun, all sorts of RF energy, just light, heat, everything comes from the sun. And it comes from the sun in every direction. It goes up. It goes that way. It goes that way. It comes out from here. Like, if you can imagine that coming. You know what I mean? So, if you've got the sun here, right, it will transmit the same amount in every direction. Absolutely. Up, down, left, right, back, front, everywhere. Okay? That type of pattern is called isotropic. Okay? Isotropic. Okay? That is an isotropic radiator. What that means, the word isotropic, it means the same amount of energy in every direction. Okay? The problem in the world we live in is we cannot create an antenna that's isotropic. We can't create an isotropic antenna. We cannot make an antenna that transmits the same energy in absolutely every direction, like the sun. We can't do it. It'd be good, but we can't. So, what have we got? The simplest antenna is a dipole. You've heard of a dipole? Maybe not. Maybe yes. If you have your signal coming along a wire, and you've got like the shield, pretend that's the shield around a wire, you know. I'll draw it like that. Okay, there's, you know, your coaxial cable. You've got the conductor in the middle and your shield around the outside. Okay, that's plugged into your RF amplifier. Okay, we're creating energy, sending it down the cable, and we want to transmit it. A simple dipole would be the center conductor goes one way and the shield goes the other way. That is an antenna, and it's the simplest antenna there is. Well, simplest I know of anyway. And what happens is we have a field of energy getting created. Okay? Now that energy is here in blue. So there's energy here, and you can imagine that goes around the front as well, okay? So, you know, it's also, I can't draw that three-dimensionally, but it comes out the front as well. It's not really up the top though, and it's not really down the bottom. Okay? So what we've got, we've just made an antenna that transmits like this. So if I'm the antenna, I'm that dipole there, I transmit within this area, you know, the sort of the area here, not above me, not below me, but in a sort of area, in all directions like that. Okay? And that's called omnidirectional. Okay, so right here, that's our omnidirectional antenna. Right. So can you see the difference in the way that that energy will get transmitted. When we have the sun, we have an isotropic radiator. So equal energy in absolutely every direction. Okay? We can't make one of those. In the physical world we live in, we cannot make that. So this is a simple one, omnidirectional. And it just doesn't go above and below. Okay? So you've got energy all around that way. Are there any questions on that? Just, do you get that concept? Can you see that? Oh yeah, that's all right. It's a pretty good drawing actually, if I must. Okay? Right, so if we have...
Maybe you'd like to look at the vertical of the omnidirectional.
Sorry?
The vertical and the horizontal, since you already
Yeah,
draw the horizontal.
yeah, maybe. I've got to see... I don't want to overcomplicate things just yet. I want to make the simple stuff clear, because this is really fundamental. And that is a dipole antenna. Okay? So if this has energy going into it, it will transmit like that within my hands. It will transmit there in every direction. Okay? Not above. Look, in the real world, there'll be something above. It might have bounced off that wall, or you might be so close to it you'll see it. But really, you wouldn't plan that. You plan for your devices to be within its beam. So what we can say is 2.14, 2.15. Just a moment. What we can say is the gain of that antenna dBi. Okay, what that means, this is the number that confuses a lot of people, but I'll explain it. Every antenna that we make, every antenna that exists, has a value of dBi. Okay, now that I got a green pen. No. This I right here means relative to an isotropic. Okay? We can't make an isotropic antenna, but every antenna we make is relative to the perfect one of 1. Okay? The isotropic we call a gain of 1. Okay? It's our base point. So what happens, we've taken energy away from the top and bottom, but we've put it to the sides. So the sides are a little bit bigger than 1 now, okay? If this was equal everywhere, it would be an isotropic, it would be 1. But it's not. We've taken some energy away from the top and bottom, and we've therefore put it to the sides. So the gain of a standard dipole is 2.14 dBi. So what that means is of the same energy of an isotropic, on a dipole, we have more gain. Now, my next statement is absolutely fundamental. And if you only remember one thing, remember this. Antenna gain means antenna directionality. Okay? That's what antenna gain means. Don't think gain is like the volume switch of an amplifier. Not with antennas. I'll write that down. Antenna gain equals antenna directionality. Okay? So what I mean by that, if you had more antenna gain, if you had an antenna with 24 dBi gain, immediately, what do you know about the type of antenna that might be? That's a lot of gain, okay? 24.
Very narrow.
Yep. It means that we've only got the same energy to start with. We have not changed this RF amplifier. What we've got here is the same, okay? Now on our antenna, if we put a 24 dBi antenna on there, we're not creating energy. All we're doing is focusing it now. We're using the energy that's coming at the end of that wire and making some sort of pattern with it. So if we've got a 24 dBi antenna, I can tell you that's probably a dish or a grid antenna, okay? Where it's focusing, we don't care about the left, the right, the back. We want to focus it all down here. That's even more than a Yagi probably. That's probably a dish, because I've got one. I've got a 24 dBi grid, and it's really focused. There are even more, but that would be a high gain antenna. So let's say we have our 24 dBi antenna, right? There's our cable. The RF is really only going there, okay? That might be a dipole here, and we're just reflecting all the back and sending it forward as well. So instead of having RF on the left and on the right, we might just reflect this and send it back there. So now you've got twice as much going that way. You see what I mean? But again, we have not created more energy. We're just focusing it, directing it, okay? And that's through antenna design. What that also means though, is there's no signal back here. If we've sent all the signal back there, over that way, we can't be sending it here at the same time.